at first glance, you might think this problem is a three-dimensional problem because it's talking about an airplane. However, there's actually no lift mentioned in the problem. It says a plane is headed 30 degrees south of east at 400 miles per hour relative to the ground. If a 25 mile per hour wind is blowing due south, find the velocity, direction, and speed relative to the air. So it's not talking about ascent and descent. So this is actually a two-dimensional problem, kind of masquerading as a three-dimensional problem. So we have north here, we have east here. We know that the velocity relative to the ground is ending up here. I'm kind of exaggerating this a little bit. That's a 30-degree angle, and we know that this is a magnitude of 400. This is the velocity with respect to the ground. And then we know we have a velocity due to wind blowing due south. So that's this direction. And that's 25. And that's velocity due to the wind. Now the velocity due to the wind is actually easy to calculate. Because it's due south, it's 0 and negative 25. No muss, no fuss. And the velocity due to the ground is not hard to find either, because we've learned how to do that. Because we're sitting in the xy plane and we know the angle, and we know the magnitude. So we know that it's 400 cosine of negative 30 degrees, because we're in quadrant 4, that's negative 30 degrees. 400 sine of negative 30 degrees. Okay, now key to this is that this was the ground given to us, and they're asking us for the velocity with respect to the air. Now remember the rule. The velocity with respect to the ground is equal to the velocity with respect to the wind plus the velocity with respect to the air. These two component pieces make this velocity with respect to the ground. But we already know the velocity with respect to the ground, and we know the velocity with respect to the wind. We're looking for VA. So that means that VA is equal to the velocity with respect to the ground, take away the velocity with respect to the wind. Okay, so that would be, let's see, velocity with respect to the ground. So that would be 400 cosine of negative 30 degrees well, let me draw it this way. 400 sine of negative 30 degrees minus 0, negative 25. Let's see if I can fit it in there. There we go. Just managed it. Okay, so we can make Desmos find these things for us, right? I mean, we're not going to do this, or Desmos or Maple, you know, whichever. I'm just going to keep using Desmos because I have it on hand. So 400 cosine of negative 30 is right there, and the sine, 400 sine of negative 30, now minus a minus, because it was minus a negative 25, is actually plus a 25, right? Because we're subtracting negative 25. So that makes negative 175. So our numbers are approximately 346.4 or 0.41 and negative 175. That's the velocity with respect to the air, and that would be in miles per hour. I just wrote them back behind here. All right, one part is done. We found the velocity with respect to the air. Now we want to find direction and speed. Well, speed is easier, so we're going to do speed first. Speed is just the magnitude of the velocity with respect to the air. So that would be the square root of 346.41 squared plus 175 squared. I'm using an approximation sign here because, of course, we're rounding this a bit. All right, so if we want full accuracy, we can put copy and paste this in. It won't really matter, but 175 squared. That worked out so nicely because, of course, the sine of 30 degrees is a half. So that's why that's working out beautifully. So that gets us 388.1 miles per hour. That's our speed. Lovely. Now all we need is direction. Okay, so to find direction, we have to remember that the tangent of theta is v2 divided by v1. It's the y component divided by the x component, which would be negative 175 divided by 346.41. All right, so theta is the arctangent of that ish. Sometimes theta doesn't work out. So when you find this angle, sometimes it's perfect, which in this case it will be, because we're in quadrant 4. But if you were in quadrant 2 or 3, you'd have to do some finagling to make it work, because arctangent doesn't give an angle in quadrants 2 or 3. Arctangent can only lead to an angle in 1 or 4, because it has to be a one-to-one function. Stuff you learned about in pre-calc. So let's see here. Let's find the arctangent. So the arctangent of 175 divided by 346.41 gets us an angle of about 26.8 degrees. Okay, so now think about the direction, right? It would be in what quadrant? Oh, I just realized I forgot my negative, of course. So it's negative 26.8 degrees because it has to be in quadrant 4, right? So it's ending up negative. Okay, so that means that the direction would be 26.8 degrees south of due east. Just think about for a second what's happening here. You have some velocity vector, 346 negative 175, which is going to be here. That's the velocity due to the air. And then you're pushing downward, straight down, with your velocity with the wind to end up over here with your velocity respect to the ground. So when you find that angle, what you're finding is this angle right here. It's some component of that 30 degrees. Right there. So the 30 degrees is the full angle from the positive x-axis down to the velocity vector with respect to the ground, and the negative 26.8 is just that piece to get to the velocity with respect to the air. All right, again, let's do another two-dimensional one. So we have a canoeist knows that she can paddle at a steady rate of 4 miles per hour in still water. She heads due south in a river with a current. She actually progresses 10 degrees east of south at the rate of 3.2 miles per hour relative to the shore. So relative to a fixed point, right? The shore would be the ground. Find the velocity, direction, and speed of the current. Okay, so let's think here. We have north right here, east right here, south right here. So she knows that she can paddle at a steady rate of 4 miles per hour in still water. All right, so she knows that she can head one way, and she's heading due south in a river with a current. She actually progresses 10 degrees east of south at the rate of 3.2 miles per hour relative to the shore. So we got two things going on here. So this whole she can paddle at a steady rate, that business, that's her vector, right? So she's heading due south right there. So that's her right there. That's the velocity with respect to the boat, if you will. So that's the velocity for the boat. It's got a magnitude of 4. So the velocity with respect to the boat is 0, negative 4, because she's heading due south. Due south. And then she actually progresses relative to the ground. So it's another one where we know the ground. So the ground is 10 degrees east of south at a rate of 3.2 miles per hour relative to the shore. Okay, so I'm going to exaggerate this slightly, but that's 10 degrees east of south. The magnitude of this is 3.2. So I've really not drawn this to scale, and I'm sorry. Maybe here's what I'll do. I'll make this velocity vector bigger for the pink one. So it's got to be longer than the 3.2. So let me kind of go all the way down. So that's the 4. So the 4 is right there. So it's bigger. And then, of course, this is a canoeist, so she's not going to paddle, you know. She can't go as fast as a boat with an engine. All right, so 3.2, and that is 10 degrees right there. Okay, so the velocity with respect to the ground would be 3.2 cosine of the reference angle and 3.2 sine of the reference angle. Now, notice I didn't put 10 degrees in there because it's not 10 degrees, right? What's the angle we're going to need? Well, if this is 10 degrees, this angle here is negative 80 degrees, and that's the one we're going to need. All right, so now remember what we've learned. The velocity with respect to the ground is equal to the velocity with respect to the boat plus the velocity with respect to the current. And the current is what we're actually looking for here. So that means the velocity with respect to the current is equal to the velocity with respect to the ground take away the velocity with respect to the boat. Okay, so that would be equal to 3.2 cosine of negative 80 degrees, 3.2 sine of negative 80 degrees. Take away, I don't know if I can fit it in, 0, negative 4. I managed it. Okay, so let's find what that is in a decimal approximation. So let's grab our handy dandy program and make it find some stuff for us. So 3.2 cosine of negative 80, 3.2 sine of negative 80, and we want to subtract a negative 4, so we want to add 4. And then, just to preempt ourselves, we can see the values here. So we know we're going to need to take that value and square it, plus this value and square it in order to find the magnitude that we know is coming. So I'm just going to get these in here right now. There we go. Okay, so we know that the velocity with respect to the current is positive 0.556 and then positive 0.849, and that would be miles per hour for both of those components, right? Because this is velocity. So there's the velocity. They also want speed, which I just found. That's the magnitude of that velocity, which is the square root of 0.556 squared plus 0.849 squared, which got us rather a small number, 1 point something. Let's go back and look at it. So 1.014 miles per hour. Okay, so there's the speed. Now, as to direction, we need a reference angle, right? Not the 80. That's the velocity with respect to the ground. There's another angle here that we can't see. So we need to use this velocity with respect to the current. And the tangent of theta is v2 divided by v1, which would be 0.849 divided by 0.556. That means that theta is the arctangent of those values divided. Okay, so let's grab Desmos and make it find that for us. All right, so I want the 0.846 on the top, and I want the 0.5556 on the bottom, and I get an angle of 56.78 degrees. So 56.8, if you will. I believe it was negative. Oh no, it was positive. Of course it's positive. Sorry, I was not thinking of that correctly, but yes, it's positive. Okay, so this is 56.8 degrees. Okay, so what's happening? Well, what's happening is your current is going this way, right? If you think of the end of the forward one and that one, it's going to be like that. And so it's forming an angle of 56.8 degrees. Now, I grant you it's not the right magnitude, but it's close. You get how that goes, right? So it's pretty small, right? Because she's pushing hard enough to go 4 miles per hour, but the current's kind of pushing her back. And that's why she's only going 2.2 miles per hour at a little bit of an angle, because the current's kind of pushing her along. So the direction of the current, right, not of her, but of the current is, when I should have said that up here, this is the direction of the air, right? Not the person, right? Because the person is the VG, right? The person in the plane, right? So the direction of the current is 56.8 degrees north of due east.